In this video, we'll be looking at the binomial distribution. The binomial distribution is a graph of all possible binomial probabilities for a given problem. So for the problem on the screen, a coin is tossed 30 times. What is the probability of tossing blank heads? So all of the possibilities of numbers that could go in that blank are from 0 to 30. We could toss 0 heads, we could toss 30 heads, or somewhere in between. Now to create this graph, what we would do is calculate the probability of obtaining each of those numbers of heads. So we'd start with calculating the probability of 0 heads, and then 1 head, 2 heads, 3 heads, so forth and so on. And each of these possibilities is just calculated with a binomial probability, the same way we did in the last unit. The way we did this in the last unit was with the binom PDF function of the graphing calculator. And so that's what all of these probabilities are, all the way from 0 down to 30. And then all of those are graphed here. Now, let's say we wanted to find the probability of 19 or more heads. The way we would have done this in the probability unit would be to find the probability of 19 heads, probability of 20 heads, 21 heads, 22 heads, all the way up through 30, add those all together, and that would give us the probability of 19 or more heads. And we can do that pretty easily here since I've already calculated all of those. So if we sum up all of the probabilities from 19 to 30, what we get is a probability of about 10%, 10.02%. Now, we would have to calculate quite a few probabilities to get that number, and we can actually find a very close approximation by using the normal curve. So I'll overlay the normal curve on top of this binomial distribution, and we can see that it's a pretty good approximation. So another way that we can do this problem is by using the same method that we did for the normal distribution. So what we'll have here is normal CDF, lower bound of 19, upper bound of infinity, which we'll write as 1e99. Now, we know that the most heads we can flip is actually 30. But that's on the binomial distribution. On the normal distribution, there is no maximum. So we do need to use infinity if we're using greater than, negative infinity if we're using less than. And then, of course, we need the mean and standard deviation here. And those weren't given in the problem. For our binomial probability problems, we have formulas to calculate those. So the mean is n times p, where n is the number of trials, so in this case 30, and p is the probability of success, which in this case would be 0.5, the probability of tossing a head. So that gives us a mean of 15. Our standard deviation is found by taking the square root of n times p times 1 minus p. In this case, that would be 30 times 0.5 times 0.5, and take the square root of that. I'll just write that as the square root of 7.5. And so we can put that into the calculator. So lower limit of 19, upper limit of infinity. For the mean and standard deviation, I just left those as the exact formulas. We don't actually need to simplify those at all. We can just type them in there just like that. And if you don't have this menu option, you'll type them in the exact same order. You'll just select normal CDF. You'll type in your lower bound of 19, upper bound of infinity, your mean, and then standard deviation. And so what we get is 0.072, about 7.2%, which is a bit shy of the 10% we got in our actual answer. And so why is that? Well, if we look back at our distribution, if finding the probability of 19 or more heads by using the normal approximation, what we're really doing is finding the area from this line over. So that area right there. And so we can see we're actually missing part of 19 right here. And the reason for that is because what we're dealing with here are actual intervals, not exact numbers. So binomial probability problems always have whole number increments. So we could get, for example, 18 heads, we could get 19 heads or 20 heads. We could not, for example, get 18.2 heads or 19.6 heads. Those just aren't possible answers. The normal curve represents things that can be measured in fractional units, so something like time or length or height. All of those would be continuous units. Binomial probability problems are going to be whole number things. So number of coins tossed. If you were shooting baskets, there would be a whole number of baskets that you could shoot. So we need to account for this by looking at the actual intervals rather than the numbers themselves. So if we look at the intervals, if we look at the 19 interval specifically, the 19 interval goes from 18.5 to 19.5. We know it goes 0.5 in either direction because 19 has to be right in the middle, and it's 1 unit wide, so it makes sense for it to go from 18.5 to 19.5. So really what we want to find is the area from 18.5 over. So if we go back to our graphing calculator, we go back to our distributions and normal CDF, change our lower limit to 18.5. What we can see is we get an answer much, much closer to our exact answer. Our exact answer, if you remember, was 0.1002. Using this approximation, we got 0.1006, so a very, very close number.